Okay, so welcome back. We have been spending the last several weeks discussing many of the properties of the real numbers, many of the topological properties of real numbers. In particular, compactness has been playing a big role, and I've given you some idea of why it's important. Really, compactness, you think of it as a finiteness condition, right? It's sort of the next best thing to being finite. And today we want to start talking about sequences. And so this will actually bring us to be developing concepts like continuity, continuous functions. What does it mean for a function to be continuous? That's defined in terms of limits. And so we have to say what it means to take the limit of a sequence. Okay? Before we do that, I would like to issue a correction to something I said last time, which I just realized I was using a terminology in a way that's perhaps not the way that most people use a term, and I just wanted to make sure that this was addressed. So if you recall, one way to describe compactness, one characterization is in terms of something called the finite intersection condition. And I just want to clarify, the way I've been using a finite intersection condition is at odds with how it's normally used. So let me just state the finite intersection condition. So the finite intersection condition is basically, you say a collection has the finite intersection condition. A collection of sets has the finite intersection condition if any finite subcollection has a non-empty intersection. Okay, so we say some collection of sets has the finite intersection condition if any finite subcollection has a non-empty intersection. Now, I think what I did last time is I stated the finite intersection condition as this together with a conclusion, and the finite intersection condition is just the part that is just this hypothesis that if you have a bunch of sets, it has the FIC if any finite subcollection has a non-empty intersection. And then the characterization of compactness can be expressed as follows. So there's a theorem which says a set is compact if and only if any collection of closed sets. So any collection of closed sets K alpha, and the way we will say it is that has the finite intersection condition, has non-empty intersection. So this is like what I said before, but I'm just clarifying that the finite intersection condition is just the hypothesis part. Okay. And last time we saw why compactness implies this, and I encourage you to think about why this implies compactness. Okay? So that's just to make sure that I made that correction in your notes. Willie? That means every, yeah. Otherwise I would have said there exists. So maybe we should be more precise here. Every collection of closed sets that has the finite intersection condition has non-empty intersection. So I'm demanding that I'm only looking at collections that have the FIC. Okay? Because there certainly could be some collections that don't. Namely, take two disjoint closed sets. Certainly they would not satisfy the FIC, and I'd be demanding nothing about them. Okay, Good. So that's I wanted to clarify with respect to compactness. So we're beginning the next chapter in the course in the book in Rudin, and we want to discuss the idea of a sequence. Okay, we've actually encountered sequences before, right? When we started talking about countable sets, we said, "Oh, okay. Well, can we list it in a sequence?" So really, what is a sequence? Well, it's something that we've already defined, but let me just say it again. Recall what a sequence is. Now, normally we notate a sequence by putting little braces around something like P sub n. So we're indexing a bunch of points, and we'll be in some metric space X. So a sequence P sub n in X, what is it? Well, it's really a function, isn't it? Like most of the objects in mathematics, we can define in terms of functions. So it's a function. Well, what does the function do? Well, the function actually takes a natural number to the nth point, right? So you can think of it as a function that goes from the natural numbers to some point in X, so the metric space X, and it maps some point, little n, to the point P sub n, a point in X. Okay, so that's what a sequence is. And we're doing this in the general context of metric spaces because I don't want you to just think of sequences of real numbers. Okay? At some point, we're going to start thinking about sequences of functions, right? So if you're a physicist or an engineer, you'd be interested in waveforms and whether they converge as a sequence. Okay? So this is the way I'm going to encourage you to think about sequences. So let's just maybe begin to address some of these issues. So, you might have, for instance, let's think here. How about, let's just imagine ourselves in the plane. So that's a metric space given by, let's say, Euclidean metric. And, we want to understand what it means. What does a sequence look like? Okay, here's some point X. And, you've got a bunch of points here moving around. Okay. Now, of course, that sequence of points appears to be doing something, right? So I might have, P1, P2, P3. It's in some metric space. Now, again, this is a schematic of points in the plane, but we could also be talking about points in a space of functions where each of these things is a function, and asking, do these things converge? So there's the real question here. Maybe I'll put that here. What does it mean for a sequence to converge? There's the question. Okay, well, clearly the picture I've drawn here, would you say that this sequence, if just informally thinking about this word, would you say that this sequence I've drawn here converges in the plane? It does? Why? Why does it converge? What makes this look like it's doing something that you might call converging? It's getting closer to some point. Yeah, so when we're talking about convergence, at least in this picture, it appears to be getting close to something. Yes, that's true. Maybe I'll call this point P. So let me label this picture example 1, because I'm going to refer to some of these examples later. Okay, so you would say this converges to some point P. Would you agree? Everybody agree? Not if you say yeah? Okay. Would you say that this sequence of points also converges to some point Q over here? No? Why not? It doesn't seem anywhere nearby, right? So nearness is important, right? A metric here is going to be important, right? Okay. So Daniel says, okay, I get that. Let's move on. So example 2. Let's draw another picture here. Would you say this sequence converges in the plane? Yeah, just imagine this picture going on. Keeps going. This is in R2. No? Why not? There's no point it's getting that these, okay, fine, good, get that. Let's move on. So you'd say no, this doesn't converge. What about this example? Here's again, same space, R2. But suppose that every point is the same. Wow. Okay. Dropping lots of chalk. Every point is the same. Would you say this sequence converges? Reasonable. Yeah, reasonable to say yes, it does converge. Okay. So yes, no, yes. What does it converge to if it did converge to something? P. Okay, that's good. What about this picture? What about this sequence? How about this? P1, P2. P3 is also P1. P4 is the same as P2, etc. Back, forth, back, forth, back, forth, back, forth, back, forth, back, forth. Would you say that converges? No? Well, it looks like it's getting close to this point, doesn't it? It keeps getting close. It gets close. It actually hits this point all the time. But what? But not all the points do, right? So our right notion of convergence should capture the fact that all the points should be getting somehow closer, right? I mean, the points beyond a certain place. Yes? Okay. So if you want to talk about convergence, we'd say yes to these examples and no to these examples in terms of convergence. Okay? Whatever that means. But we're still going to try to make this concept very precise. All right. You with me? Okay. So let's make a definition. Let's make a definition. What would you say is true about this picture, or even this picture, but not about this picture or that picture? What does it mean to converge? Willie? Okay. Okay. Now, I like part of what you said, which was you can get arbitrarily close, but that also is true here. I am getting arbitrarily close to this point. Okay, but to the same point, well, if you pick this point to be P, I do, at least every odd numbered time, I get close to this point. Okay. What do you mean by every point? I'm just pushing you a little bit. I appreciate you volunteering. What do you mean by every point? Because here, certainly P1 is not close to P. P2 is not close to P. P3 is not, but as you move down the index. Okay, very good. Were there some other comments here? Harris?
Well, let's say that you had something that moved out and then came.
Oh, yeah. Good. How about, sure, I'll make another example. Would there be anything wrong with this, Harris is saying? So it does, maybe this is P10, but P11 and P9 are here, right? And then they just keep going, like 1, 2, 3, and then anomalously goes out and then comes back in. Still converge, would you say? Yeah, okay. So let's make a definition that reflects this picture. Laura. Okay, so we certainly want our definition to be robust in the sense that if you truncate any of the initial portion, it should still converge if it converged before, right? Okay, good. So let's make a definition that kind of reflects what you're all saying. So here's our definition. We're going to say Pn converges if okay. Well, here's one way to describe it. If there exists a P such that, this is, of course, in the metric space X, such that for any distance you name, for every epsilon bigger than 0, so let's pick an epsilon here. You give me an epsilon bigger than 0, and it'll be a ball around P, such that for any distance epsilon bigger than 0, what do I want to say about the sequence? All these cases we said converged. There is a point in the sequence beyond which, what? All the terms are inside. Now, is that true with this example where you pop out? Yeah, it's still true, because beyond you just go a little farther, right? If this happened to be P1000, you're all the way down here, and then boom, you're out, and then you come back in, then you just go to the 1001th place. So we're going to say if there's a point, if there exists, so for every epsilon bigger than 0, there exists a number. This is going to be an index n, such that what? Little n bigger than big N implies if you're beyond n in the sequence, what's true about the distance between Pn and P? It's less than epsilon. Okay, so this is the important part of this definition. The first part is just saying, okay, Pn converges to P. Okay, and this is the index beyond which all the terms are closer than epsilon. Okay, so let's unpack this definition a little bit. It seems kind of a funny definition. Before I do that, let me just point out that if you have that definition, you often write this, if that definition holds, Pn, you could draw an arrow. Or you could also say, that's one way to say it. Another way to say it is, and you've seen this before, you write lim, n goes to infinity of Pn equals what? P. Okay, it's the first instance of the limit symbol. Okay, and now, of course, you're probably wondering, well, what's the connection between the sequence converging and limit point? What's that connection? We're going to explore in just a second. You often say Pn converges to P. That's one way we say it, right? Or another way we say it is P is the limit. Notice I'm not saying limit point, I'm saying limit of a sequence, Pn. Okay, that's another way, that's how we say this. Okay, so we're always talking, when we're talking about convergence of sequences, we can say it in lots of different ways. All right, let's do an example. How about this sequence? Pn equals, how about n minus, let's do it more easier, n plus 1 over n. And this is in what metric space? In R. Okay. Does this sequence converge? Yeah? What does it converge to? Good. You have a proposal already, right, based on some intuition. If I had said this sequence converges to 10, you'd say, no, it doesn't. Well, let's see why. Can you prove that it converges to 1? Claim Pn converges to 1. Oh, I like that notation. You don't have to write very much. Okay? The limit notation's a little more cumbersome. Okay. Why? Proof. Okay, now, what do we have to do? We have to, what does this definition require us to do to show convergence? You usually already have a candidate, so it's the green part we're interested in. Steve? Ah, yes. So to establish convergence, your task, you're given an epsilon. Your task is to find an n, right? That's always how these kinds of this definition works. It's always your task. So your task is given epsilon. So I'm going to write this before the proof. So this is scratch work. This is what we're thinking. What we're thinking is, given epsilon, our task is to find an n that works, whatever that means. What do I mean by works? What I mean by works is that satisfies this condition here. Smiley. That works in, satisfies smiley. Okay? Okay, so you claim that this sequence converges to 1. Really? What's the distance in, how are we going to measure distance in the real line? Take the difference, absolute value of the difference. Okay. And you're trying to find me an n so that this difference is always less than epsilon. So we're still doing scratch. This is not even a proof yet. I still need some more space for scratch. So here we go. So notice, do you see that we want to bound? We have to bound what? N plus 1 over n minus 1, right? What we really want, what we want is this to be less than what? Epsilon, yes? This is all scratch. We're kind of working backwards here, right? We're trying to see when is this less than epsilon. So the question you should be asking yourself is when? For what n? That's what we're asking here, okay? It's like a little bubble, okay? A thought bubble. When? When is this true? What is n plus 1 over n? 1 plus 1 over n minus 1. Would you agree that this is the same as asking when is 1 over n less than epsilon? Again, the same thought bubbles. When is this true? Well, 1 over is always going to be positive, so I really don't have to worry about the absolute values. That's true. Good. And what condition does that put on n? Good. Would you agree that if I take the absolute value signs off, which I can do since this is always positive, that this is the same as, again, this is all still scratch. This happens when epsilon, 1 over epsilon is, n is bigger than 1 over epsilon, yes? Okay, now, I have an understanding of when this bound holds. Can you tell me now, is there a point in the sequence beyond which this condition always holds? What is big N? Yeah, how about letting big N be anything bigger than 1 over epsilon? Then, if little n is bigger than big N, it'll be bigger than this. Good. So, our proof. Where does the proof start? Yeah, so here's, I like saying it this way. Given epsilon bigger than 0, your job at the beginning of the proof is just to tell me what n works. You don't have to show your train of thought. None of this has to show up. This is the scratch work you do beforehand, right? Your job is to answer the question. What was the task? Find an n for any epsilon. Oh, okay. Let's choose big N to be equal to, how about 1 over epsilon? I'm going to just make this slightly bigger, make the ceiling of 1 over epsilon, just to make sure it's a natural number. Yeah, it doesn't really have to be, but it's nice to think of it as an integer because it's an index. So traditionally, if you look at your book, it actually says there exists an integer n. Actually, it should be a whole number, right? Yeah. And so it's helpful to it's always traditionally thought of as a natural number. Okay, good. So choose n, and now you just have to demonstrate why this works, right? So how are we going to demonstrate that? For if, so we're just kind of saying, okay, well now take a look. N is bigger than big N, then n is bigger than 1 over epsilon. We're getting to be grown-ups now, so I'm assuming, and you can assume, the reader can make this jump, right? N is bigger than, you don't need to write out n equal the same thing, n equals this. You just showed them this, right? So now you just tell the reader n is bigger than 1 over epsilon. Do you think that the reader can make this jump? All I did was take off the braces. Right? Okay. Oh, okay. So then what? Is it true then that this distance is less than epsilon? Well, we know we're going to need this fact, right? So hence, I'll put a comma, hence 1 over n is less than or equal to epsilon. Okay. And now I'm just slightly worried because I have a less than or equal to, and I am somewhat, I would actually like this to be strict. So I'm going to come back to this and fix it if needed. But let's just see what happens. Hence that. So now we're just going to establish the bound we were asked to establish. The distance from Pn to P is n plus 1 over n minus 1, which, again, you can expect the reader to do that. You don't have to show that much work, 1 over n. But this is definitely less than, well, yeah, it's less than or equal to epsilon. And so I want to actually make this strictly less than. So how can I adjust this to make this strictly less than? Yeah, how about adding 1 here? Then this is definitely strictly bigger than 1 over epsilon. This is definitely strictly less, and we have the desired inequality. Okay. Laura. N greater than 1 over epsilon? Yes, you could fix this in multiple ways, right? You could say let n be strictly bigger, but yeah, you could let it be strictly bigger. You could also, yeah, you could do that. But I like this because it's being explicit about what n is. Yes, Bonnie. Well, if n is bigger than 52, is it bigger than 51? Yeah, so I made a jump here, which you might, if if you were worried the reader couldn't see, then you should probably write it down. You'd say n is bigger than this, but this is bigger than 1 over epsilon, strictly. Okay? Good questions. Laura?
I've heard another definition where you say if little n is strictly bigger than big N, so like the original definition.
You could do that too. Yeah, I'm just agreeing with the definition, Rudin's definition. Okay. Lots of ways to fix that, but it is important for this to be strictly less than epsilon. Okay, great. So if we feel we have a handle on these ideas, let me put up some statements here, and I want you to decide if this is true. These are true or false. Jenny. Well, I guess you might worry that so if it's not strictly less than epsilon, then so really what we want this, if we want this to agree with the topological definition, the topological definition involves open balls. And in that case, we're really demanding that Pn lives in an open neighborhood of P. Yeah. Okay. Excellent question. Let me write down some statements, and I'd like you to decide if these are true or false. Okay. So I'm going to write down 6 statements, and you decide if they're true or false. Statement A, is it true that if Pn converges to P and Pn converges to P prime, then P equals P prime? True or false? In fact, let me write this as an implication here so it's easier to see. You have to decide if that's true or false. Second statement, if Pn is bounded by the way, what do I mean by Pn being bounded? I mean that as a function, its range is bounded. So all the points that are actually achieved lie in some ball. Okay, so the range of Pn is bounded. That's what that means. If Pn is bounded, does that mean that Pn converges? Statement C. If Pn converges, does that mean that Pn is bounded? Statement D. If Pn converges to some P, does that mean P is a limit point of the range of Pn? There's a question. Couple more, and then I'll give you some time to discuss this. E. What about the converse? If P is a limit point of some set E in X, does that mean there exists a sequence that converges to it? There exists a sequence, let's say Pn, in E, such that Pn converges to P. There's a question. And then the final question is, if Pn converges to P, does that imply that every neighborhood of P contains, let's write this, every neighborhood of P. Does this mean that every neighborhood of P contains all but finitely many Pn? All but finitely many. there's a question. Okay, so I'd like you to take a few minutes while the video takes a break. I'd like to take a few minutes to discuss with your neighbor in twos or threes which of these are true and which of these are false. Okay? And if you're not talking with somebody, do talk to somebody because I'd like you guys to discuss this. Hi. How's it going? Feel free to come in and sit in if you like. Oh, okay, awesome. Is this a tour group? Awesome. Yeah. This is real analysis. It's analysis of the real numbers. It's a math major course. So, okay. Do you guys need a little more time? Have you decided? You've decided? How many people have an answer to part A? Some kind of answer. Excellent. Excellent. Okay, so Maggie, what do you think the answer to part A is? True. You think it's true? How many people think it's true? Okay, well, yeah, you're good. Very good. True. Excellent. Part B, who has an answer? Nice. Keith, what do you think the answer is? False. Okay, that's good. Why is it false? We're going to answer why all the true ones are true, but the false ones you probably can dispose of quickly. Good. Example 4, this has got a bounded sequence, right? The points all stay within some ball, but they don't converge, so C4. Nice. Example C, who has an answer? Fewer people have an answer. Lindsay, what do you think the answer is? Ah, okay. How many people think the answer is false? How many people think the answer is true? Well, let's see. We'll come back to that. Good question. That's a good place to maybe stop for now and try to answer some of these questions. So why is it true in part A? You have a sequence that converges to something. Maybe, here's the kind of thing that could happen. You could imagine a sequence that seems to be getting in close to some point P. Yeah? And maybe it's also getting close to some point Q. So, okay, obviously can't do that out here, right? But, maybe it's some other point that's like really right next to P, there's another point, Q. Like maybe it's just like the next point over. No next point over. But okay, let's see. Why can't that be the case? Katie. Okay. Okay, nice idea. There is some fixed distance between P and Q. So I'm going to blow this picture up if you don't mind, because it can be blown up. Q is not right next to P, whatever that means. So this is this part blown up right here. Okay, so this poor sequence has to make a choice. Something like that, right? But now you're suggesting using what for epsilon? Okay, yeah. So your idea is, let's call this distance whatever it is. Do you mind if I call this epsilon? And then we'll maybe, one way to do this, and certainly a good way of doing it, is to focus on a distance epsilon over 2. Right? And by the way, when you apply this definition, do you see that this says for every epsilon? So what that means is you can choose any epsilon you like. You can make this answer, this endpoint here, if you want, epsilon over 2. You could make it 27. You can make it pi, right? Okay, so good. How do we make this concept precise? What do I do? I see the intuition. So now where's the contradiction going to come if they were, in fact, different? Well, eventually, past some point in the sequence, past the, let's say, 17th term, they're all in here, yes? But I could also draw an epsilon over 2 ball around Q, yes? And past some point in the sequence, they're all in here, yes? What's the contradiction? Maybe past the 17th they get in here, and past the 52nd they get in here. Yeah, well, doesn't that mean if I take the bigger of 52 and 17, all the terms have to now be in both balls? But the both balls are disjoint, which can be proven by the triangle inequality. Okay? So we're in good shape. That's basically a good argument. But notice there's a key technique here. So given epsilon, so we're not given. We're gonna apply that definition because we're assuming they converge, right? So assume Pn converges to P and Pn converges to Q. Let's let epsilon equal the distance between P and Q. Then, because of convergence, that's my epsilon. There exists an n, let's call it n1, or maybe np, that's the one associated with p, such that little n bigger than np implies, I'm going to permit me to give me some space here, implies the distance from Pn to what? P is less than, what am I going to put here? Epsilon over 2. You can't stop me from doing that. This is exactly what we want. Notice I could put anything here. The other thing I want you to notice is, because of convergence, I just zoomed directly in on there exists. How come I didn't have a for every epsilon here? I chose one, right? In fact, the epsilon I chose implicitly isn't epsilon, it's epsilon over 2. Okay? But this is perfectly fine to write out. Presumably, if the reader sees this, if they've been following along, they'd realize, they're appealing to this convergence. Okay? But if you want, you could say, because Pn converges to P, this is true. But there's no need to write it here because you just said it about 2 lines ago, right? You can assume the reader can jump a line or 2 without you having to repeat stuff, okay? I'm only saying that because a lot of you on the exam repeated stuff that was just like a line or 2 away. You don't need to do that. Okay, what's the second thing I want to write down here? Also, say the same thing, but now there's an n sub q, such that n bigger than n sub q implies what? dPnq is less than epsilon over 2. Okay, we're almost there. There's a key idea here. There's no contradiction yet until you look at the 17th and beyond the 52nd, and you say, wait, beyond the both of them, so let's take the max. So here's the thing. We'll let n equal the maximum of np and nq. I want you to notice this step. This is such a key idea. This kind of thing happens a lot in analysis arguments. You know, when you're dealing with convergence, these 2 things have to be true. Let's look at the bigger then. If you look at the bigger of them, then anything beyond, for anything beyond, both of these have to be true. And that's a problem. Then n bigger than big N implies what? Oh, look. Oh, this is so wild. Look. I have a point that's supposedly in here and supposedly in here. There's lots of ways to get this contradiction, but one is just to say, look, I have Pn, distance to P, Pn, distance to Q, both strictly less than epsilon over 2, and yet the distance from P to Q is what? Is epsilon, and now we have a problem. Then, okay, so then for implies what? Well, let's look at the triangle inequality. Pn to Q. First, epsilon equals the distance from P to Q, but the distance from P to Q is less than or equal to the distance from P to Pn plus the distance from Pn to Q. Do you see what I'm doing here? I'm claiming that if there was some point P that's in both of them, like secretly right here, its distance has to be less than what? And this one has to be less than epsilon over 2. And so what do you have on the right-hand side? Strictly less than epsilon over 2. And this is epsilon. And so what do we see here? We see that epsilon somehow was strictly less than epsilon. Problem. A contradiction. A contradiction. Okay? Everybody happy with that? Notice also here, this strict became important. Okay? This would not have gone well if this had been a less than or equal to in the definition. Okay? Of course, that all happened because topologically speaking, open sets are important. All right? There's actually another way to do this. Proof. I'm just going to mention this because we did this in some ways as a proof by contradiction. Oh yeah, well, we didn't even say that though, but how is this implicitly a proof by contradiction? We assumed this is bigger than 0, right? Let epsilon be this, and we assume P is not Q, so epsilon is bigger than 0. Okay. Now, if epsilon were equal to 0, then we couldn't use this definition, right? So everything was fine in the case they were equal. But you could have done this not as a proof by contradiction. The other alternative would have been just to start here. Notice that these things have to be true, and then show that the distance between P and Q has to be 0. By showing that the distance between P and Q, what is this going to say? By triangle inequality, distance between P and Q has to be less than epsilon for every epsilon. What's the only number that's less than epsilon for every epsilon? If epsilon's positive, it's 0. So then, because the distance between 2 points is 0, the points must be the same by the property of a metric. Okay? Could also do it that way. That's in fact what I have in my notes, but since you guys came up with it, that's good. Okay, we've already established B. What about C? If it converges, is it bounded? Well, how many of you thought the answer was true? Okay, the trues have it. Can you see why? Follows from what? From F. Okay. Yeah, let's at least give a hint as to why C is true. So the pictures go something like this. It converges. And it converges to, let's say, some point here, P, yes? And for any epsilon, blah, 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 there's a point beyond which all the points are inside, yes? So, do you see why the sequence has to be bounded? Past the 47th position, they're all in this ball. So how many other points are there? 46. Finitely many. Okay? So that's basically the idea. Yeah, so just use epsilon equal 1. Then there exists an n. Why? Pn converges to P. So there exists an n such that little n bigger than big N implies the distance from Pn to P is less than 1. I just chose 1. Okay. Oh, great. So then let R be the maximum of 1 and the distance from P to P1 through the distance from P to Pn minus 1. That's good enough, right? Ah, thank you. Big N. Minus 1 if you want, but if I throw in that last one, it won't matter. It's still a maximum. Okay. And I can take the maximum because this is a finite set. You don't need to write that anymore. People are okay. It's enough to just realize that, okay? Now, you do need to point it out. If, for instance, this wasn't finite, then you'd have to justify why this is maximum or why, or say it's a supremum or something, right? Okay. Great. So then what? This is it. All points. So all Pn are in this ball of radius big R around little p. Done. Happy with that? Okay. Okay. Let's see about the others here. D, true or false? BR, it should be an open ball. Okay, yeah, so I see where you're going with this. Meh. How's that? Excellent, thank you. The worry was that one of these points would sit on the boundary. Okay. Okay, great. D, if a sequence converges to P, does that mean it's a limit point of the range? How many people say true? How many people say false? Well, it's false. Thank you, Adam. Why is it false?
You have an example like example 3 up there, where it just lands on that point immediately. Then, you can't always find a neighborhood around it. There's another point besides that one.
Excellent. Okay. if it's sitting on top, it can't be its own limit point of its range. Okay. So while the concepts are related, they're not exactly the same, right? Convergence, P is a limit point of the Pn, but P is not a limit point of the range of Pn. Okay? P is a limit of Pn. Limits and limit points are different concepts, but related. Why are they related? Look at the other condition statement, E. True or false? It's true, turns out. Why? If P is a limit point, well, let's just look at this picture. Suppose P is a limit point of this sequence. Sorry, suppose P is a limit point of this set, E. Tell me how I find a sequence that converges to P. How about pick a ball of radius a half? And then there's a point inside, yes? Then take a ball of radius what? A third. Take a point. A fourth point. Fifth point. Do you see these points have to converge to P? So choose Pn in a ball of radius 1 over n around P. Choose a sequence of Pn, and then Pn converges to P. And then we're in good shape. Okay, I'll let you justify that, but I'm sure you can do that now. It follows easily from how we chose the points. Okay, good exercise. I'd like you to do that. Okay, what about F? True or false? If Pn converges to P, then every neighborhood of P contains all but finitely many points. True. Do you see this picture? Sort of gives the idea. Everything's in a ball, and then everything else is out. So that's certainly true. So let's label this. It's enough to see why this forward direction is true because of smiley. It turns out the reverse direction is also true. Why is the reverse direction true? If every neighborhood contains all but finally any Pn, I claim that means that they converge. Pn converges to P. Why is that? Well, you have to find me a big N for every epsilon. Yeah, so basically, look, if it contains all but P1 through P47, then what? I'll let N be 47. Okay. So this means that the converse is also true. Okay. I won't write that down, but think about it and see the book if you want it written down carefully. I'd encourage you to just write it down yourself. All right. Okay, so we've talked a lot about sequences, and what I want to do next time is we want to talk about sequences in R or in Rn. What can we say about their convergence? For instance, you take a limit of a sequence. In R, you can talk about summing two sequences. Is the limit of a sum the sum of the limits? There's a natural question. Is the limit of a product of sequences product of the limits? These are questions we'll begin to tackle next time. Okay? Great. I'm going to pass out the exams now, and we'll resume the taping next.